Hi everybody, as promised, what I'm going to do is make a short video for each question. I made a video on the specimen paper and I had to rush through it because it was over 1 hour. So what I'm going to do is make smaller videos for certain questions so I can explain them a little bit better. That way you can use this for more learning as opposed to just finding out what the answers are, okay? All right, so let's look at number 1. It says a monoprotic acid, HX, is found to have the following composition by mass. So we got 39.9% carbon, 6.7% 3 hydrogen, and 53.28% of oxygen. All right, so let's see what it's asking us for. It wants the empirical formula. The empirical formula is just the smallest whole number ratio of moles. All right, so let's just say we're talking about water, H2O. We have 2 hydrogen for every 1 oxygen. And so 2 moles of H for 1 mole of O. Okay, so when I teach this to my students in the Chemistry 1 class, what I do is instead of talking about moles, I talk about dozens, right? If I had 1 dozen water molecules, I would have 2 dozen H and 1 dozen O. The mole concept is exactly the same, so 2 moles of H, 1 mole of O. So basically what I got to do is just find out how many moles of each of these things I have. So if you look in the data booklet, moles is mass divided by molar mass. So let's go ahead and do that for each element. So the number of moles of carbon will be equal to its mass. Now, when we're not given mass here, we're given percentages. But if I had 100 grams of this acid, then that would be 39.99. So anyways, 39.99 divided by the molar mass of carbon, which is 12.01. When you put that into your calculator, you get approximately 3.33. Let's do the same thing now for hydrogen. So the number of moles of hydrogen will be equal to its mass, which would be 6.73 divided by its molar mass, which is 1.01, which gives us 6.6 moles of hydrogen. Finally, for oxygen, it is 53.28 grams divided by the molar mass. Remember, this whole diatomic element thing, oxygen and hydrogen are both among those elements, but it only counts with, sorry, I can't even think. A rule only applies when they're in their elemental form. So a lot of kids, what they'll do is they'll divide by 32. All right, so anyways, when you do that, you get 3.33. Now, for you IB students of the world, the IB would not mark that if this was your IB exam. Everything has to be within the boxes, so make sure that you control the boxes. When you take your IB exam, they give you an extra booklet if you need to move, if that's not big enough, but don't do what I just did there. All right, so anyways, I see that there's 3.3, 6.6, and 3.3. We got to get the ratio between them. To get a ratio, you take the smallest number in the set. I have 3 numbers in the set, and divide it into all the numbers. So for carbon, 3.3 divided by itself is 1. 6.66 divided by 3.3 is 2, so that makes 2 hydrogen, and 3.33 divided by itself is 1, so that means 1 carbon, 2 hydrogen, and 1 oxygen. All right, now notice here we have question 1A and B. Something tells me that B, C, D, everything that comes after that for this question is going to be concerning this monoprotic acid HX. All right, so part B does say 25.00 cubic centimeters of a solution containing 1.51 grams of HX is titrated with 0.75 molar solution of sodium hydroxide. The HX is, key term, exactly neutralized by 22.30 cubic centimeters of the base. Determine the molar mass of HX. So the most important thing to know here, since we're asked for the molar mass, is what is the unit of molar mass? Well, molar mass, which is denoted with a capital M, is the number of grams divided by the number of moles of the substance. Well, we are given the number of grams here, So all we need to do to solve is find out how many moles of HX we have. Well, remember, if it's exactly neutralized, then the concentration of H plus is equal to the concentration of OH minus. Okay, so when it's neutralized, it's equal. All right, so basically, we got to find how many moles of the base we have, and that will be equal to the number of the acids. All right, so when we're calculating the concentration in the US, we just use a capital M. You can see why they don't do that in the IB world. Right? Will be the number of moles of HX divided by the volume of the solution. All right, or well, the moles of NaOH, but they're equal. All right, so that means volume times concentration gives us moles. So when we're calculating the number of moles of NaOH, all right, we have a concentration of 0.750 times a volume. Please note that volume is in cubic centimeters. We have to have it in cubic decimeters, so we divide by 1,000. So times 0.02230, that's just the volume. And when you do that, you get 0.0167 moles. That's number of moles of NaOH, which is equal to the number of moles of the acid. So I just take, to get the molar mass, the grams, which is 1.51, and divide by the number of moles, which we determined was 0.0167. And when you do that, you get 90.4 grams per mole. And that's your answer. All right, state the molecular formula. All right, well, how do we do this? Well, remember, this is the mass of the molecular formula. The molecular formula will always be whole number divisible by the mass of the empirical formula. Because if we double the number of each subscript, then we double the number of each atom or element. Sorry. If we triple them, and so forth. So all we basically got to do is see how many times bigger is the compound than its empirical formula. So we have to first add up the mass of the empirical formula. It's CH2O, so that'll be 12, plus 1 times 2, plus, Jesus, I'm losing my mind, plus 6. So it's 12 for carbon, 1 times, plus 16, sorry, I'm losing my mind. 12 is the molar mass of carbon. Hydrogen has a molar mass of approximately 1, and there's 2 of them, right? And oxygen has a molar mass of 16. I was thinking about the number of valence electrons. So when you add all that up, you get that our empirical formula has a mass of 30. That's 3 times smaller than 90. Right? So our molecular formula is 3 times larger than our empirical formula. So the molecular formula is C3H6O3. And there we go. All right, so part D here says HX reacts with aqueous sodium hydroxide. That's a little bit redundant because that's what they told us up here, but whatever. And we're given an equation for this. Identify a functional group in HX. All right, so if it's a functional group, that means this is an organic acid. And an organic acid has a carboxyl group. Now, in the new curriculum, the IB wants you to get away from memorization. So if you know that each organic acid ends with the COOH, you could write that as well. Right? Or you could maybe even draw out the structure, which is a carbonyl bonded to a hydroxyl. I'm assuming any one of these would give you the right, give you the mark. Those two things are what were in the mark scheme, so we'll have to see. All right, so continuing on with question number 1, it gives us the infrared spectrum, and it asks us to identify the functional groups responsible for the absorption bands shown at Y and Z. All right, so I didn't prep well. Got to grab me a data booklet. And as soon as I'm done making this video, I'm going to listen to the song that's stuck in my head. All right, so we're told to go to table 20. Table 20 is infrared stuff. So we have here is the bonds, the type of molecule it is, the wave number, which is just the x-axis, and the intensity. It just shows how long it goes. All right, so let's first do, the one thing I did not like about my old video is my yellow pointer in the way all the time. All right, so Y is a broad absorption compared to Z, which is a little bit sharper. So broad just means it's like that. All right, so let's first do Z. So if that's 15, that's 16, 17, 18, 19, 2000. So we have Z as an absorption right around 1700. Most of the students taking IB chemistry around the world should recognize that that is the absorption for the carbonyl in either an aldehyde, ketone, carboxylic acid, or ester. All right, so if we see that strong absorption at 1700, that's for the C double bond O. Now, when we look for Y, what we see here is a broad absorption that the lowest point of it is right around maybe 33, 3400 wave numbers. So when I look in the data booklet, I'm going to look at that range. Ooh, oh, it could be an OH in an alcohol and phenol. But we have a carboxylic acid here. Oh, well, if it's an OH and a carboxylic acid, it would be between 2500 and 3000. So I know that this is for OH. The beautiful thing is, if you look at the mark scheme, it doesn't ask for which particular one. It just wants the functional group responsible, and it's OH. Now, if you had written out carboxyl, you would technically be wrong here. That's actually a hydroxyl group, and I'll explain why when we actually draw the structure, which we're asked to do next. All right, so it's got to be consistent with all of the evidence. Well, first of all, we know that the molecular formula of this compound is C3H6O3. 3 oxygen. That might actually account for this hydroxyl group up here. All right, so we know there's 3 carbons. We know it's a carboxylic acid. When in this situation, what I like to do is start by just drawing the functional group. So our functional group is COOH. That takes care of 1 carbon. Now, this carbon has 3 bonds, so it itself can only be bonded to one of the other carbon atoms, and regardless of where you put the bond, the third one will be right there. All right, so I know that all these carbons will take 5 total bonds between themselves and different things. We got the 3 carbons. We got 3 oxygen. Well, there's only 2 oxygen there. So one of the things that's bonded to must be an oxygen. Now that oxygen can't be alone, so it itself is probably bonded to a hydrogen. Something tells me Y is for that and not that. All right, so then we'll have 6 hydrogen total. We've already got 2 there, so 4 more. Oh, there's just 4 bonds left for those hydrogens. So perfect. All right, so we have 2 OHs in there. This OH would make an absorption. Where is it? Right there, or somewhere between 2500 and 3000. You can see in Y that it's past 3000. The other OH in the alcohol or phenol would be between 3200 and 600. It's broad, right? So that tells us that Y is for that one. Again, they don't ask. If they don't ask, don't tell. All right, so number 2 is about an experiment. It's all about how we can use models to model the behavior of nature. All right, so this is all about Rutherford's gold foil experiment, where he took a thin piece of gold foil, and he shot alpha particles at it. Remember, alpha particles are the nuclei of helium atoms. If you have just the nucleus, you have just the protons. So those are positively charged particles, just a heads up. All right, so they were accelerated toward a thin sheet of gold, and the paths were detected, giving evidence of the positive charge of the nucleus. Okay, so the number of particles detected at different angles. So let's just look at this thing here. We shoot the alpha particles as a thin sheet of gold. Some get bounced back, some go straight through, and some get that angle from there. All right, so if we look, the number of alpha particles detected at different angles of deflection are shown. Let me refocus here. Good. Well, that looks so much better. All right, so the number of alpha particles, if we look here, the angle theta is the amount of deflection. A majority of the particles took path 1, going straight through. A smaller number of particles had larger angles, and as you get to blah, 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 I'm done talking. So explain why some of the alpha particles followed path 2, rebounding from the gold sheet. So there's path 2. They went in and bounced back. All right, and the reason why, I would say, is the alpha particle struck the nucleus. I mean, most of what we talk about in general chemistry has to do with electrostatic attraction and repulsion. So like charges are repulsive to each other and opposite charges attract. All right, since alpha particles are positively charged and the nucleus, as we are told in the beginning of this problem, is also positively charged, the alpha particles, I would say, collided with the nucleus and were repelled. Now, explain why some. If it says explain, you want to give a full accounting. So I would say by the positive. So positive alpha particles collided with nucleus and were repelled by the positive charge of the nucleus. I mean, to me, that's a good answer. When you look at the mark scheme, it's much less detailed than that. But if you're asked to explain, you have to give all reasons behind what you're saying. Right? So that to me means you should talk about the fact that the alpha particle is positive and they bounce off. All right, so most of the alpha particles pass right through, undeflected, suggests a conclusion that could be made about the structure of atoms. Well, let's assume that you're throwing tennis balls at a brick wall. If you throw 100 tennis balls at the brick wall, if 98 of them go straight through the wall, but 2 of them bounce back at you, the only assumption you could make is that most of that wall isn't actually there. If a tennis ball can pass right through it, it's not there. But if a couple of balls bounce back, there is something there, but because most didn't bounce back, it's got to be really small. So what that actually told him is that atoms are mostly empty space. Compared to the volume of an atom, the volume of the nucleus is insanely small. For example, if the nucleus of an atom were a marble, just a standard size marble, about 1 centimeter in diameter, and you put it on the 50-yard line at a football stadium, if the marble's the nucleus, the football stadium itself is the atom. The lighting kind of makes it look like I have a mohawk. I don't. All right, so moving on with question 2. It said helium was first identified by analyzing spectra of solar radiation. Outline the appearance of the emission spectrum of helium. All right, so all emission spectrums look pretty much the same. It's a series of colored lines on a black background, and just we're only asked to outline here, so I probably don't need to say this, but I'm still gonna, just in case, that converge at higher energy. Unfortunately, this is just one of those things you kind of got to know. All right, so moving along, emission spectra are one-electron systems and can be explained using a model with the electron attracted to the nucleus by an electrostatic force. This model predicts that the electron occupies discrete energy levels. Some levels for a helium cation are shown. All right, so explain how the frequencies observed in the emission spectra support the idea of electrons occupying these discrete energy levels. All right, so explain, and it's 2 marks. So there's got to be 2 things they want us to say. All right, so first things first. What I would say is the lines are produced. You know, I'm going to pause. All right, so if you read what I wrote here, it says, well, let me just explain it first. the helium cation only has one electron, and its ground state is n equals 1, the first energy level. If it gains energy, it jumps up to an excited state. Now, it has to absorb energy in order to move to a higher energy level. But all matter will always head in the direction of less energy. So less energy is more stable. So an electron that has more energy than it should is unstable. So it will fall back down. And when it falls back down, the energy it absorbed is given off in the form of visible light. The length of the transition tells you, I should say the length of the transition corresponds with the color. A bigger distance moved in this energy level diagram indicates a greater amount of energy absorbed, which means a greater amount of energy released. And if you look at the rainbow, Roy G. Biv, the blue side is the high energy side, and the low energy side is the left-hand side. So when I look here, I said the lines are produced when the excited electrons return to a ground state. Only certain colors are possible, so only certain transitions exist. In other words, if an electron could travel from anywhere it wanted, you wouldn't get an emission spectrum, you would just get a continuous spectrum or a rainbow. All right, final page in this particular video. It says deduce the ionization energy of the helium plus ion from the energy level shown. All right, so for you HL kids, n equals infinity represents the amount of energy needed to be absorbed to be removed from the atom. So n equals infinity represents the ionization energy. All right, so a ground state electron has negative 5250. Notice n equals 0, or n equals infinity is 0. That means it just takes 5,258 kilojoules to make that happen. Suggests 2 reasons why the ionization energy of the hydrogen atom is significantly smaller than the ionization of the helium cation. So remember, if we look at a hydrogen atom, it has 1 proton and 1 electron. Well, this helium cation has 2 protons and 1 electron. Since it has a greater positive charge in the nucleus, it pulls more strongly on those electrons. So the helium cation has a greater nuclear charge. Now here, that's pretty much all you need to say for the 1 mark, because you're just asked to suggest. It doesn't ask for a reason why you're suggesting it. Also, if you look at the trend in atomic radius, it decreases going left to right. So the helium cation is also smaller than the hydrogen atom, which means that the electrons are physically closer to that stronger nucleus, makes it harder to take them away, which is why the ionization energy is greater. It suggests why the model outlined in BII can predict the emission spectrum of He+, but not He. A couple things here. First of all, we are told that emission spectra of 1 electron systems can be used to explain the model. Well, a helium atom has 2 electrons. Remember, the lines in the emission spectrum are produced from electrons moving about. Each atom has different spacing between their energy levels and different numbers of electrons. So the distance between each colored band in your emission spectrum will change depending on what you've got. And also, once you take away that electron from the helium atom, all the energy levels kind of compress a little bit. Right? So it says in the mark scheme, electron-electron interactions have to be taken into account. But I think only works for 1 electron systems would be best. I mean, for crying out loud, that's their wording. All right, so finally, outline why models have evolved over time. Well, the gold foil experiment on the beginning of this question was from 1911. So Rutherford had an alpha emitter, something that could shoot alpha particles. Well, the first person to propose, propose that matter existed as smaller bits called atoms was Democritus, and that was thousands of years ago. He did not have an alpha emitter. So I would just say new evidence has been gathered. You could also say new technology has allowed us to measure more precise stuff. All right, well, that's that. So hopefully the more detailed video is helpful, and 25 minutes is certainly better than an hour and 25 minutes. So thanks for watching. No, I don't know when I'll do the next one, maybe tomorrow, but I'll see. The bottom line is I ain't going to do it at home, so I'll have to try to find time during the school day. But yeah, have a good one. Bye.